Everything else going on at SuperCompute 25 was interesting. You have to understand this is an academic gathering. It's been subsumed by everything AI, sure, but the academics that I met here were excited because even if we're in an AI bubble, we've built all this compute. And I trust the AI academics to come up with interesting uses for all of this compute for everything outside of AI, scientific compute, research, you name it. First up, AMD was showing off their plan for Helios. That's the name, that's the plan for their open compute rack scale AI infrastructure. It's a double wide rack. It's sort of a new rack design, but this is how they're going to build it.
Helios, AMD Helios. They've got kind of a demo, kind of an interactive thing, but I want you to notice some things when I pull out the drawer. First off, look at all those memory channels. Look at that. There's 16 memory channels on this platform. That's interesting. I mean, it could be 8 memory channels with 2 DIMMs per channel, but really, we know. But also the networking fabric. This Ultra Ethernet stuff is one of the most interesting aspects as we look at, sort of the whole ecosystem solution that AMD is building. We know MI400. We expect MI400 to be amazing when it comes to performance and inferencing and everything else. AMD has to be showing this to partners, and this has to be what's driving some of the partner investment interest stuff that we see, sure. But that's not the whole story. The whole story is connecting everything together, running it, and building that with a software stack. We get a little preview of that with some of the updates to ROCm and everything else that's going into that. But I think the most interesting pieces here are the memory bandwidth. Look, it's a single socket in each one of these drawers, and yet, it looks like there's 8 interconnects here, plus also the new stuff that we look at from the fabric, Polara and Pensando, and the networking aspect of this. There's a lot of interesting little details you can notice here, some of which have been hinted at, some of which have been announced, and some of which are not yet on everyone's radar. But the details are there if you look for them. Core Instinct, there's your processor. That's a lot of memory channels. Notice the memory channels. But your network interfaces are here. Volcano AI NICs, PCIe Gen 6 and UA Link. Instinct GPUs, MI450, CDNA up to 432 gigs of HBM4 per GPU. And then here is your fabric interface. Ultra Accelerator Link over Ethernet. 72 GPUs in a rack. So your compute and GPUs, and then your fabric interface, the other side of the 16 interfaces we just saw coming in here. Everything is connected to everything else, because that's how you have to do it. And this is in that double width open compute standard, so, delivered and configured as a unit, I'm sure. I'm at Gigabyte, I'm with Liam. Remember Liam, he's in all the videos. There's a lot of cloud stuff happening here. Look at that, it's the NVIDIA partner badge somewhere here. But this is not NVIDIA, this has nothing to do with NVIDIA. This is actually Ampere. This is their 1U platform. You can do inferencing with it. We can make it about AI. But I think that relegating Ampere to just AI and inferencing, they've got a lot of opportunity. This is a neat platform.
The simple 1U, Ampere 1M processor up to 192 cores. It's very popular. They're starting to get into AI inference workloads because they can handle, if it's like 10 billion parameters or less, they can handle on a CPU. You don't need to have a GPU.
Pretty reasonable memory bandwidth for their platform.
Yep,
Pretty reasonable connectivity.
Mm-hmm. Yeah, so this is a really exciting platform they've just introduced this year. We've got about 10 models that support the Ampere 1M series of processors, so it's pretty cool.
Yeah, it is really nice to see good performance and good release cadence from Ampere. And so it's always nice to see partners supporting Ampere for that kind of thing, because some companies are all about ARM. Some companies are all about density and deploying things. And I think I found my new multi-node game server. So this is what is like a multi-blade chassis? Like what do you call it?
Yeah, it's our first Blade series. We have the new B series we've introduced, and this is a 10U. It's a 3U 10-blade server that supports the EPYC 4005 CPU, but we also support the LGA 1700 Xeon.
Look, it's my beautiful, beautiful AM5 socket. So this can run your Minecraft server with multiple M.2 ports. You have dual memory channel. You've even got some PCIe connectivity here. You wouldn't run a GPU in this, but you could run high-speed connectivity. This would make a fantastic Linux box, cPanel servers, this kind of thing. This is the kind of thing and the kind of density that we see like the medium and large hyperscalers replacing. But in terms of like 10 node for like a small business Proxmox server, this would also make a pretty reasonable platform for that use case. And so it's nice to see more enterprise engineering go into something like that. Gigabyte's gone a little off script. This is actually 2 AM5 sockets on a single PCB. This is 2 systems in one drawer. Each system has a dual 25 gig interface, so we have 4 25 gig interfaces in one of the blades. There's not any interconnectedness or failover or anything like that. You're handling all that in software, but you can do that on a 50 gig fabric.
Yeah, so that's what's pretty cool about this. It's again the same 3U size chassis, but now we're doubling the amount of sockets that we can support. Because yeah, we're using liquid cooling, and inside we have an inner manifold, so it kind of simplifies it. So when the liquid's coming in, you just have one liquid of cool liquid coming in, one warm going out. So you don't need to have 10 tubes of cold and 10 of hot. So it's pretty cool that they've simplified the design. And we'll see more of this product later this year, probably towards the second half, early Q.
AM5 in this kind of custom design. Someone is spending a lot of money to do custom AM5 design. That should tell you what the market demand is. It's kind of nuts to see something like this.
Yeah, this originated out of a demand. It was a particular demand by somebody, and that's why we've developed it.
Who could be replacing lots of sockets with lots of AM5 sockets? I wonder.
This is Gigabyte's RTX Pro 6000 chassis. 6 RTX Pro 6000s in a traditional rack configuration. By default, each card's running at 300 watts, and there's also a Bluefield 3 DPU on the end there. This is what one of Gigabyte's GB300 NVL72 trays looks like. It's all liquid cooled and copper interconnects with 8 E1 flash storage bays in the front. NVIDIA controls a lot of the aspects of the design here, so this doesn't look a lot different than all the other GB300 NVL72s, but that's kind of the idea. But for x86, the Gigapods, Gigabyte has more flexibility. Side by side, the AMD solution with direct liquid cooling and the NVIDIA solution also with direct liquid cooling. Gigabyte Gigapods, which this is something interesting that I'm keeping an eye on. I mean, check this out. DDR5 DIMM throttling, not here. They've already preemptively built in heat sinks for the DIMMs. Modular, reusable, liquid cooling technology. And if you look, these two racks, there's really not a lot of difference in the liquid cooling infrastructure between the sides. So we're supporting 2 completely different AI universes with a lot of reusable parts. Love to see that kind of engineering.
This is awesome. So what do you do when you deploy your data center, but then the utility company can't get you electricity in time? Well, you can deploy a turbine. I mean, it's a lot easier to transport natural gas or diesel or whatever. Mitsubishi has their M501G gas turbine. Not even joking, this is part of the reason, this kind of thing is part of the reason why there's a shortage of turbines in America, because this makes it easy to put power wherever you need it. So it's like, we've got everything, we got connectivity, we just can't get quite enough power to scale as quickly as we want. This solves the problem. I'm always looking for new technologies that let me move PCIe devices farther away from compute. And NEC was showing off a really cool demo where the GPU from over here behind 2 kilometers of fiber is connected to this system, and it doesn't know. The PCIe fabric is sort of handled transparently. The PCIe frames are going over Ethernet, but it doesn't know. This is the Network Operations Center for the Network Operations Center. What do you do when you're at SuperCompute? It's academic research, and you need 1.6 terabits back to Oak Ridge, and some other people have their 800 gig and their 1.6 terabit connections. 10 gig distribution. I'm here with Bart. He's here to explain everything.
Hey everyone, my name is Bartosz Drogosiewicz. I represent the University of Warsaw ICM in Poland. So today with Wendell, I will be explaining to you how this network actually works, and I will try to get into as much nook and crannies I can in my allotted time I have.
Scientists like to go fast. There's so much fiber.
It's so much fiber. So here currently we are at the main stage. This is so-called the main stage of the SciNet. SciNet is an organization that is responsible for building the world's fastest temporary network. We do this every year at this conference, and we make use of the equipment that vendors are donating to us. So not only equipment is donated, our time is also donated. We are volunteers that help build this network and make this conference happen.
And the scientists can run experiments while they're here to see, can we do quantum entanglement over the public switch fiber network?
That was actually the experiment last year. And I can tell you a bit more about that later, but yes, we also do that, exactly.
I remember.
Yeah, we also have, on our website, there is an NRE list, so if anybody's interested, there is a list of the experiments we conduct here using this highly advanced equipment and those super fast networks.
I understand the network this year is also a lot shorter and fatter than last year.
Yes, so every year we change our technologies and topology. This year it's more streamlined, especially in the case of the main conference network. We also last year have branched out into two separate networks. We have Science DMZ and Core Network. They have separate AS numbers, and that helps us basically build one network that is more reliable and simpler for the 1 gig, 10 gig connections we have, and the cutting edge technology, highest speeds, the fastest things we have for the researchers right here.
Now, there's a lot of universities here, but undergrads as well as graduate student researchers and student clusters. There's a whole student competition. It's like who can spin up the best mini cluster. It's like, here's our Beowulf connection. We got a connection back here, and you have to provide all the infrastructure for all of that.
Yes, so actually the equipment for student cluster competition is donated by their team sponsors. So the actually interesting thing about that is that they have to work within some constraints, like power constraints, not only time constraints, performance constraints. They cannot just bring in the most powerful equipment they have and run it at 1 megawatt. They have to basically work within specified measured limits.
Nice, yeah, that's a lot of fun. What's the coolest thing? Like, what's the first thing you should notice, or what's the coolest thing?
Okay, the coolest thing that I rarely see anywhere else is the Polatis switch. That's the big white thing in the rack 4 that has connected fibers to it. This is basically a programmable level 1 switch. You can tell it that it can switch without plugging the fibers back and forth, that you want the connection go from port 1 to port 16, for example. And the best thing is it's I think $250,000 piece of equipment that you can operate from your smartphone. I've seen a guy do it.
Well, that explains why the network's a little simpler this year.
Yes, I mean, we basically have the Polatis every year, right? We also have introduced last year and this year also in our mini HPC cluster, we actually have a petabyte of storage right here on the stage.
So what is it like? How many years have you been coming to SuperCompute?
So I have been coming here for 5 years helping build this network.
How have you seen it evolve from scientific compute and like AI taking over the universe? You think we're in a bubble? What are your thoughts on the evolution of SuperCompute?
That's actually a very interesting question. Like in the 2021, I think when the conference was back here, it was mostly like after COVID, and so it was very constrained and small, but you still could notice that there is like still a paradigm shift towards quantum. Next year was the AI boom. But what's interesting is that everybody can know where you can buy chips. Not everybody knows how to cool them. This is why, especially this year, last year, you can see a shift in conferences like this, not necessarily towards the chip makers, but for the manufacturing of cooling. So everybody can build a 1 megawatt data center. Not everybody knows how to properly operate it and cool it and how to handle power delivery and stuff like that.
Oh yeah, I've definitely noticed the power delivery and cooling. It is really wild to see folks here that have things like, oh, your local utility where you are can't give you enough electricity for your dream data center. Here's our jet turbine you can have on site for a couple of years while they're building out that infrastructure. And you have companies like Eaton that are showing, I mean, they feel like the belle of the ball because like we make power and power distribution systems, and now it's like, wow, this is like really upscale power and power distribution systems.
Yes, some people that try and design data centers do not realize how much is a megawatt, how much is a 10 megawatts, how much is 100 megawatts. What do you mean I cannot have redundant power coupling to my data center, right?
I know a guy that he saved a piece of wire that like it was vaporized and black, there was a little bit of it left. But the reason that happened is because all the GPUs in the data center woke up within the same like 1 millisecond window. And the power grid wasn't designed for that.
Oh yes, this is especially a problem that I have heard about on conferences like this. Basically, what do you do when a 10 megawatt data center goes suddenly down and then tries to boot right back up, right? So some power grid suppliers and power plants are big into this problem. Like they're basically telling some customers to, hey, you need to do something about that. It's killing us, basically. Yes.
It's wild to see this. You know, thanks for the tour. Thanks for introducing yourself. This is awesome. SuperCompute is about supercomputing and not necessarily like it's been commercialized, I think, but it's nice to see the academic and the research component.
Yes, that is exactly what we are trying to do here. We are trying to push the envelope forward and maybe tell everybody how cool this is.
Cool, thanks. Thanks for joining me.
Thank you.
Hi, Wendell. Nice to meet you.
Nice to meet you again.
Finally.
You're working on all kinds of exciting stuff with XE, CSS, and Liquid, what was it?
fluid simulations.
Fluid simulation.
Fluid X3D. So
Fluid X3D.
I'm Moritz Lehmann. I work at Intel. I'm the engineer behind the XeSS super resolution and frame gen GPU kernels.
I saw that on mobile.
Yeah, I recently made it compatible even with Meteor Lake, despite Meteor Lake hardware lacking the XMX unit. With all the optimizations, I got it fast enough to run on the MSI Claw first gen, which is absolutely amazing for all the people who bought it already. And here at Supercomputing, I'm also with the Fluid X3D software. I'm wearing it. So this is my own software. I do it as a hobby project. You can run aerodynamics, aeroacoustics at very large scale. Last year I demoed it on Xeon 6 running in 6 terabyte memory with over 100 billion grid cells.
That's the same 8800 setup we were using for AI, but he's doing it with 6 terabytes of memory, probably one of the largest installations, because inferencing on AI and computational fluid dynamics depend on random memory access going fast.
It's absolutely mind-blowing that we have such large memory capacity on a single computer already. And this year at Supercomputing, I'm demoing Fluid X3D on multi-GPU with the Arc Pro B60 workstation GPUs. Over at the Intel booth, we have a workstation with 4 of them to pool together 96 gigabyte VRAM. So that lets me run and render 1.8 billion grid cells in real time. That's a special thing. Industry can only dream about such large resolutions, and I'm running it in real time even.
Yeah, B60 already up and running for scientific compute. I'm still working on SRIOV, but B60 is pretty exciting to see a 96 gig pool just hanging out.
Yeah, and that is the software is written in OpenCL, so this is universally compatible with all of the hardware, from low-end toaster hardware that is 15 years old up to the highest-end data center GPUs. You can even put AMD, NVIDIA and Intel GPUs in one workstation and have them run together, pooling their memory. It's like a cursed version of SLI.
And you're putting it on GitHub.
And it's on GitHub. It's for free for educational and research use.
Nice.
Go try it out.
Very, very awesome. Very nice to meet you, and thank you for the shirt.
You're welcome.
Thank you.
Nice to meet you.
I ran into a wild Allen, and it turns out that Solidigm is showing off liquid-cooled M.2, and it sounds insane, but they're 25 watts. There's 5 of them here. This is like 125 watts of cooling that you have to deal with, and if you've got an all-liquid-cooled server, what's going on? Yeah, so you can have the giant heatsink, or you can have more room for more E1 drives. And the mechanism...
Running cooler.
Yeah, running cooler. The mechanism moves a thermal pad on and off of the metal. It's kind of nuts.
It's good stuff.
I also ran into Cornelis Networks. Yeah, OmniPath. Remember the video that I did on OmniPath? This is a competitor to InfiniBand. I'm keeping my eye on them, and they were showing off their 400 gigabit networking platform. This network is already in use in certain supercomputers. It was part of the build out for supercomputers, so they're going to be around for a long time, but I want to see where they go from here. I want to go fast. I want to use this network, not just for CUDA, but also maybe something on the AMD ROCm side of things. I think it's possible. This has been a wrap for SuperCompute 2025. I had a lot of fun in St. Louis, and I get to hang out with some old friends and make some new ones and get the inside scoop to understand how academics are using this fancy new hardware for AI research and, well, basically any academic topic. See, I want to understand better what's going on, how it's being built, and how the pieces fit together. And this event was tremendous for me in terms of leveling up my understanding of how people are using the tools today. I don't want just the marketing stuff. I want to understand how these academic institutions, universities, and businesses are using these tools, the new tools, like how it all fits together. So making those connections and making friends with people and getting access to systems is a big part of why I went to this event. I'm Wendell, this is Level 1 Techs, and I'm going to see you in the next one. If you have any questions or I miss anything, feel free to hit me up in the forum. I'm signing out, and I'll see you there.